Thanks very much for the warm introduction, Graham. So one of the occupational hazards of talking about mathematics is when you abbreviate it, you get told off. Because in the US, it's math, and in the UK, for unknown reasons, it's maths. But I actually think us Brits, sadly, have a point. Because I think there are actually two subjects of math, or maths, today. So I think the plural, unfortunately, is the accurate term. You see, at the one end, we've got maths out in the real world, maths in society, which is more widely used, more important, and, in a sense, more popular than ever before in human history. And at the other side, we've got math in education that is more despised, less creative, and sort of disliked by everyone involved, be the teachers, students, feared by governments as to how it can screw up our economies. So there are two maths, and in a sense, this talk is the story of the two maths. And just to be clear, the kind of maths you see in the real world is all about modeling, lots of things that you're trying to answer problems for. How do you solve this? How do you set this up? There's a lot of creativity. Math in education looks a little different. Lots of writing stuff by hand. If you're lucky, add a calculator in. That's kind of the very different styles. Lots of calculating, not actually working end things out. So what's the difference between these two? Well, it's pretty simple. Computers. You see, math in the last decades in the outside world has fundamentally changed as a subject. And the reason it's changed is because it's based on computers these days. In education, we haven't done that. The computer is somehow, at best, an add-on. The thing isn't based on that. And that is the fundamental chasm that's opened up between the outside world and education in math. So let me take that a bit further. Let's start by asking, why do we learn maths? And in particular, why is everyone in the world in an education system pretty much forced to learn math? Why is it such a mainstream central subject? Well, I think there are about three reasons that one could argue for that, particularly the mainstream subject. Reason one is technical jobs. It drives our economy. It's crucial to our economic development. Number two, it's kind of, the world has become a far more quantitative place in the last decades. It's kind of hard just to survive in a modern society if you're not pretty good at sort of being quantitative and mathematical. And kind of one of the amusing things is even stuff nowadays that sort of doesn't necessarily look like math, often is. Let me open up here. What I was meaning to do, which I forgot to do in my setup, was I will open up Wolfram Alpha, and we'll ask a question, am I fat? And if we ask such a question, in the modern world, these sorts of things are quantified, right? I mean, in this case, it's assumed, unfortunately, a weight rather below its default weight is below mine. I think mine's more like that, but I'm a little taller. And, we're going off and we're getting a quantitative result for that. You'd never have dreamt, really, of doing this kind of thing in a quantitative way as the general public a number of years ago. But now you do. And I'm actually just about in the normal range there. So I guess that's good news. That was, of course, engineered. So those were two reasons why you would learn math. And I think the third, which is critical, is what I might call logical thinking. Math has been a sort of critical way over hundreds of years in which people have structured thought in a logical way. And again, that's a critical reason why it's important for everyone. So when we say we're doing math or learning math, what are we actually doing? Well, I think there are about 4 steps to this. The first one, which is completely screwed up most of the time, is asking the right question. What is it? What is the problem we're actually trying to solve? Have we distilled down the question we really want to ask there? Secondly, let's take that real world or theoretical world picture and turn it into a mathematical form. What's the equation, what's the expression that represents that in a way that we can use the power of mathematics to then transform to an answer? So step 3 is indeed that transformation, which we call computation. And step 4 is kind of going the other way. Take the computed result and turn it back into the answer in the real world. And there's a crucial step, 4B, which is verifying it, checking, did we get the right answer? Does it make sense or not? So guess what we're doing today in school? We're spending about 80% of the time on step 3, by hand. Yet that's the one step computers can do vastly better than any human, even after years of training. So instead of making our students into third-rate computers, what we should be doing is using computers for doing step 3, almost exclusive. There are edge cases where I think hand calculating is still important, particularly mental arithmetic and estimating and things like that. But for the most part, we should assume computers as the default for calculating, and we should focus students on these other 3 steps that are almost entirely ignored in school education. The crucial point to understand, math is not equal to calculating. It is a much bigger subject. Now, why has this all got confused? Well, actually, it's not that surprising, because for hundreds, thousands of years, the limiting step in doing mathematics, as I've described it, was calculating. You know, you had to do it by hand. There was no other way, and that was typically what limited what you could do. What's got muddled up, that fundamentally changed with computers. Computers, if you like, have made the biggest change to any ancient subject that I can think of in human history in the last decades with mathematics. Fundamental to the subject has been computers do the calculating. So I think of calculating as the machinery of maths. It's the thing you'd like to get around if you could. It's just that for thousands of years we couldn't. Now we can. And one of the things to think carefully about is, you know, people say to me, but, you know, isn't it great that people should all learn hand calculating? That's kind of a useful thing. And I say, well, yeah, it might be great. If somebody's interested in the history of hand calculating, as I call our current maths curriculum, go ahead, that's great. Just like if they're interested in ancient Greek, like I kind of liked ancient Greek, the key question is, would you force somebody who doesn't have some interest in that somehow to go learn it? Is there a good societal reason to force them to do that? Well, you might argue there's no good societal reason to force people to do any level of education. That's a sort of question of the curriculum versus not, which has been much discussed in this conference. But let's say there are mainstream subjects that we kind of think have some real benefit for society, and you do want people to do it. You know, I wouldn't put ancient Greek in that category, and I wouldn't put traditional maths in that category, but I would put the kind of computer-based maths I'm talking about in that category for the reasons, the general purpose reasons I talked about. And just to understand the extent of the problem, my estimate is, per year, 21,000 average student lifetimes are used up learning hand calculating. That's a hell of a lot of human resource. So we better be damn sure we know why we're doing it, and we better make sure that what we're doing is justifiable. So one of the key points I want to make and distinguish, and I think this has often got muddled up in discussion about technology and education, is for mathematics, I'm arguing that there are 2 ways sort of you can think about using technology. One is to assist the process of learning. How are you changing the process of learning? And there are many great ways to do that. You know, games, other ways in which people can be distant, all sorts of things that are great. They apply to many, many subjects, whether it's history or mathematics or science or English, in different ways, but, you know, also I think personalized learning fits very much there too. But maths is fundamentally different because the subject has changed. So what I'm talking about is computer-based maths. The fundamental curriculum has changed to something where you assume a computer. Now, you can add on to that assistance, the computer-assisted maths. That's great. I don't say we shouldn't use those ways of learning, but that doesn't change the basic subject matter, and that's what I'm sort of talking about. So key point, better deployment of the wrong subject isn't going to fix the problem. And every report I've seen around the world from governments about fixing maths education muddles this up. They think, basically, that somehow if you teach it better using modern technology, you'll fix the problem. Well, you won't, because you're teaching the wrong subject. So teach the right subject and teach it as well as you possibly can, or learn it, or set people up to learn it, and I think we'll get much better progress. So that's a key distinguishing feature I wanted to make. Okay, so that's why I think we should change to computer-based maths. what do the skeptics say? Let me take 2 or 3 of the points that I typically come up with. They say you've got to get the basics first, by which I think they mean you've got to learn stuff on old technology before a new technology or something. I don't know. My big question, though, is basics of what exactly? You know, are the basics of taking a photo, learning how to process a film? Well, they were, or for that matter, coat a plate with chemicals. Okay, they were one day, they're not now. You know, are the basics of learning how to drive a car, learning how to service its engine? Well, not nowadays. So what we've got to distinguish here are the basics of the subject itself from the mechanics that you happen to have to employ at a particular point in time. And this is where the chasm has opened up. So I absolutely believe you need to get the basics of those 4 parts of maths that I described. That used to mean getting the basics of hand calculating to a large extent, but it doesn't now. That era has passed. It only does in some edge cases that I described. And if you look at how our curriculum today is labeled, you see you get to some of the nub of the problem. These are some typical headings for parts of the maths curriculum. You know, completing the square, inverting matrices, simplifying surds, okay? These are to do with the mechanics of how you hand calculate. What I think we should be doing is problem-centered mathematics. You know, design a currency. What coins and notes do you need? You know, by how many levels of friends are we separated on Facebook? Making a perfect password for your login. That's kind of a problem for every 7-year-old. How do you get a good login, a good password? It's a good way to make one up. How does code breaking work? How do I make it so people don't break it? Aesthetic questions, and perhaps the subject of this talk. What's a beautiful shape? Does maths have anything to say about that? You know, the golden ratio from Greek times. And you know, things like how much can you compress a photo or video or music before you notice? The thing with a computer is you can actually just go try these things. You can actually just do them. You know, here's a face. Let's see what happens as we compress it more or less. And, you know, see when it seems like it's got degraded. Let's go change the process by which we're compressing it. Let's go play around with the algorithm. These are actual real things in mathematics that really happen every day for which we need to know, you know, what to do. But they're very divorced from what we're doing at the moment. Another objection, computers dumb maths down. I have to say this one particularly pisses me off, okay? You know, look in the outside world. Do we honestly believe that science, technology, engineering, all the things, you know, that are technical, have conceptually been reduced since computers came along? I don't think so, not for 1 minute. Conceptually, those things have been vastly empowered, and one of the big reasons for that is because you can do much more powerful analysis and modeling and mathematics, and you can do that because you use computers. So in fact, the very reason why these subjects have so transformed the world in the last years is because computers do the calculating. We should do the same in education. And, you know, here's a typical thing I often show on this. You know, one great thing about using a computer is you can get more experience of different situations. That's solving a simultaneous equation. Many of us had to do that kind of thing at school. And by the way, I'd be interested to know anybody in the audience who has actually done that manually, who isn't in education teaching it since they left school or since they left college. But anyway, you know, the point with a computer, you can make it a little harder. I just change it to x cubed plus 2, right? It's a bit harder now. But the principle of what I'm doing there, solve equation, get an answer, use the answer, is the same. But I can actually do it with real stuff. Stuff with hair all over it. That's like the real world. So the real problem, actually, is not that computers dumb down mathematics. It's that the questions that we're setting people today are dumbed down because they are doing them by hand. And I would even argue that some of our recent crises, like the financial crisis, has some inkling, some aspect that is a problem because people assumed they had to simplify everything down. They were used to looking at very simple things rather than working with problems with hair all over them. Hand calculating procedures teach understanding. I have a little bit of sympathy with this. I think that learning how to procedurize things is important, whether you're in management or whether you're in maths. I don't think you should typically be doing it by hand. I think you should be getting a computer to do it. And there's a great way in which we do this. The way that procedures and stuff get written down today, called programs. And the way of doing it is called programming. We should be doing programming. And it's very nice to see the UK initiative recently launched to push for that in schools and to take some of the other stuff out that was pointless. See, I think of programming a bit to maths, a bit like composition is to English. It's the way of expressing your creativity. It's the way to write it down, but to actually get automation happening, to get a computer to actually do it. And, oh, I don't know, I like living dangerously, so I was going to write a little program here. I'm actually going to cheat, I hope. And I'm going to, if my network willing, as they say. What I've done is a linguistic input here to generate a program, because I couldn't be able to type it all. And this is a little program that generates an interactive plotter of what's known as beats in physics, which is when you add two waves that are quite similar. Now, it hasn't actually done exactly what I wanted, because it didn't produce the sort of range I wanted. So I'm going to put in a different range, and maybe what I'll do here is, oh, I don't know, I'll do something like, let's say, a minus 0.9 to 0.9, and we'll just write this little program. Here we go. So that's sort of what I wanted, which was a little thing to simulate what happens when I have bigger and when I have notes that are quite similar in frequency. So that's a typical way of just using a computer to get a feeling of something. Now, that's not particularly creative, but let me show you. We have a whole site full of creative, I think there are 7,600 as of today, demonstrations, as we call them. These are community-created knowledge apps. I think it's the biggest sort of set of knowledge apps in the world. And there are more fun ones here than I just showed you. This one is simulating gas bouncing around. And it's kind of fun. You can change the temperature and see what happens. And you can play with it. Now, of course, generating these is kind of interesting and fun. And so one of the things I wanted to announce today is that we have launched a programming challenge to make for UK schools and students in them to try and make the best demonstrations possible. And it'll be great, because they can go publish them on the site. They can actually have a published piece of work. So more on our site about that, but I think this will be an interesting thing to complement the government's new initiative, and I'm very pleased that we're able to do that. So at the heart of what I'm saying about mathematics is we have an opportunity now to make something that's both more practical, more vocational, and more intellectual at the same time. It's not a choice, and it doesn't need to be a choice. We need people to get the experience of maths. That's how they'll get the experience of the concepts. And there's no contradiction here between the vocational and the intellectual. One of the other things we can do is reorder the curriculum. We can teach calculus early. This was an example I made for my daughter, where you increase the number of sides of the polygon. And let's see, it turns into a circle. Now, that's a kind of view of calculus where you're making things smaller, smaller, smaller all the time to an infinite number of sides, or near enough. That's a kind of view of things we don't get. We don't usually give people until much, much older. But that's actually a very useful view of how things work. Computers can allow you to do that. I'm not going to go into this, but we have to fix assessment. The real barrier to a big change worldwide is the completely dumb way in which people get assessed. There are two ways we can still have assessment of some sort and fix it. One is it needs computers in it. And the second thing is it needs to be much more open-ended. The idea that you can have fair assessment that doesn't somehow mimic the real world in its open-endedness is a huge mistake. Just because we're trying to get completely reproducible marking. So that's all I'll say here about it, but it's a big issue. Let me just finish by saying, why now? Why should we make this big change to mathematics at this moment in time? Well, really three reasons. There is massive impetus around the world. Virtually every country believes its maths is screwed up. And, so the question is, where first? Which country is going to leapfrog the others by making this change first and quickest? The other thing is ubiquity. Computers are effectively ubiquitous now. it wasn't just that we didn't have them in place. We've actually got, the devices to hand all the time. And, that's a very important part of being able to implement this. And the other thing I wanted to come to quickly was interface. You see, one of the examples that was mentioned in the intro was the CDF, computable document formats. So the fact that you can have documents that interact, and of course the Apple announcement is a big help here in putting the infrastructure in place for that. But what you want is computable documents that actually work in real time, where you can try lots of different things in the sort of way I was showing the demonstrations. But this is a much richer way to interface with the material than existed before, and I think that's going to be a great growth. Now, another thing I will quickly try and demo is voice linguistics. So let's try. I'm going to use Siri. What are the prime factors of 3,249,328? And we'll see whether the network actually does this. But what I want to show you is just how much. 1 second, OK. I'll show you just how much. It's amazing. Just in the last few months, you can now amazingly produce. Here we go. Let me see if I can show you on my camera. You can just about see at the bottom there. There are the prime factors commanded by voice through Siri to Wolfram Alpha of that number. Isn't that amazing how the interface has so changed round in just a few months? That's how easy stuff has got. So my big plea is stop teaching calculating, start learning maths, and reach for the right maths too. And I guess this was the reaching logo for computerbasedmath.org. Thank you. Okay, good.
Thank you very much for that, Conrad. Obviously, interested, we both have young daughters, and the way you're approaching to give them calculus and so on, and my daughter building universes in Little Big Planet and so on. And yet, of course,
Similar.
About this time last year, Nick Gibbs, the State Minister, came out with a wonderful quote. Sorry, I'm having difficulty with my various devices here. He says, Nick Gibbs said, "You can't expect children to cope with complicated quadratic equations if they don't know their times table by heart. Without solid grounding in arithmetic and early maths in primary school, children often go on to struggle with basic maths skills throughout their school careers. It also means they leave school without the knowledge they need to complete everyday tasks in their adult lives. The use of calculators in primary schools must be appropriate." What would you say about that? He seems to be
I would say it's confusion to the power of confusion. I mean, basically, what's happened there is we've got maths, the subject I've been describing, confused with computation. So math's a bigger subject than computation, as I described. Computation is a bigger subject than numeracy. And they've just all got convolved together by, it's just a complete big muddle. The thing we've got to have is conceptual problem-solving ability, applying whatever is the best tools that are available. And, I always say use the real world as your guide. I mean, one of the big things about, Latin, okay, whether Latin is good or bad or whatever the reasons for learning it or not, the fact is it isn't used in the outside world in its own right now. Maths is. It's used everywhere and in a growing way. So why don't we use the outside world as our guide? But nobody's gone into this enough, or many people haven't in government in particular, to understand that the outside world changed. So what's being said there, I think, is some confusion of what might have been the case many, many years ago. I believe strongly if you stand on the mountain of automation, you get further. But you've got to understand what you're doing. You've got to use open-ended tools. Again, don't go don't go and get the computer to act all the time as the teacher. To do something. I mean, the most crazy thing, and I'll finish on this, the most crazy thing is, people who give me examples saying, look at this way, and we've got this fantastic multimedia show to get the computer to show a student how to solve an equation by hand. This is nuts. The computer should be solving the equation. The student should be figuring out why we needed the equation in the first place, what the hell they're going to do with it. And that's how we should be doing it, not the other way around. So these things have got very backwards. I mean, I think calculators, it's sort of a mixed thing, because I'm all for using whatever technology you want to use. But the trouble with calculators, they're not terribly open-ended much of the time. And so they can fall in this chasm between real maths and educational maths, as it is, unfortunately. Thanks a lot.
Bye.